It's great to be here at the 2020 PyTorch Developer Day in its first virtual instance. My name is Kim Hazelwood, and I'm part of Facebook AI Research, also known as FAIR, where our charter is to advance AI in the open and for the benefit of all. FAIR is the part of Facebook that brought you PyTorch, and it's been a pretty exciting ride since then. Popularity of PyTorch has skyrocketed, but I'm actually here to tell you just how much more work needs to be done throughout the AI systems landscape. There's still plenty of open problems and opportunities that remain. Many of the opportunities in underinvested areas become apparent when you look at several other trends in AI systems and think about the rationale behind those trends. So today I'd like to highlight a few of the trends that we've noticed and tell you how that's driving some of the work that we're doing throughout FAIR. Next, I'll talk about some of the things that we're doing to encourage others to come along on this journey with us as we focus on fulfilling that mission of advancing AI in the open. And finally, throughout, I'll highlight some of the work that others are doing in this space as well. So let's start by talking about some of the exciting trends. First, it's been really cool to see how much traction PyTorch has been able to gain throughout the research community. Given that PyTorch emerged from FAIR, it was designed with a broader research community in mind. So seeing it show up in 70% of NeurIPS papers has been pretty validating. It's important, though, to take a step back and think about what it was that made PyTorch gain traction so quickly. And the answer is simple. PyTorch is easy to use. It allowed researchers to focus on the research and not get tangled up in the framework complexity. While this might seem obvious in retrospect, it's amazing how many times we underestimate the importance of hiding that complexity and get surprised that things like raw performance aren't actually as important as we initially thought they were. In fact, history has lots of examples where languages or technologies ended up gaining immense traction despite early skepticism about other factors besides usability. People objected to programming in C because it would never be as fast as a Ninja assembly programmer. And Java, how could you possibly let the language handle pointers for you or leverage just-in-time compilation? It'll just be too slow, right? In the AI world, this has repeated itself. Before CUDA, you had to shade two triangles to do a matrix multiply on a GPU. CUDA came along and let you express your computations differently. And now we have several other examples like JAX and Julia, which fundamentally rethink how people express the computation that they want to do. These types of efforts focus on making things easier on people so that those people can focus on developing solutions to AI problems and not battling with the interfaces to get there or being exposed to the complexity of the underlying framework layers. The benefits of usability eventually caught the eye of the production world. Sure, it took a little bit longer, but that's not so surprising. The 2020 State of AI report highlighted several challenges of research to production and noted that adoption in production does tend to trail adoption within research. But this part of the story was frankly more surprising than PyTorch's adoption by researchers. In the early days of PyTorch, many would have laughed at the thought of Python getting anywhere near production. The standard underlying assumption there was that compute performance was all anyone should care about, and that with the captive audience of production-focused software engineers, usability just isn't a priority. But they were wrong. Usability does matter, and making things easier on software engineers, machine learning researchers, and data scientists frees them up to think about solving problems in their domain. That became even more important at Facebook when the number of engineers whose primary role was to train models all day, every day, started to grow significantly. At some point, we looked around, we saw thousands of engineers leveraging our systems for machine learning, and that number was growing rapidly. This meant that it became more and more important to ensure that their time was well spent and that they were focusing on actual ML problems, not fighting with infrastructure. And it seemed to be working. Their productivity started to increase at an even faster rate. And wow, look at that. The computational requirements of all that ML work resulted in an 8x increase over that same 18-month period. Exciting, right? No, that's actually a scary trend. We can't sustain that kind of growth. We need innovation to happen lower in the stack to combat that growth. That's when the accelerators came in. So McKinsey and Company published a report last year showing several interesting trends and projections related to accelerated hardware for AI. Now, looking at the AI hardware landscape, we can see that we're already in the midst of a whole lot of changes. The training landscape is becoming much more diverse, with a significant shift from pure GPU-based acceleration to a split between GPU and ASIC acceleration. And on the inference landscape, which used to be dominated by general purpose compute, is shifting now towards accelerated systems, primarily in the form of ASICs. Now, keep in mind, this ASIC category isn't one type of ASIC with a shared set of instructions, compilers, and tools available. Every ASIC is different and has a different ecosystem and has to be optimized differently. Well, what's the problem with that, you ask? If we look back through history, when new hardware appears, usability tends to lag significantly. We forget the lessons of the past, and we assume that users are much more capable and willing to spend effort unlocking the performance of new hardware than they actually are. And there's also a tendency for that complexity to bubble up into the upper layers and complicate things. Remember that story I told you about the early days of GPUs and having to shade two triangles in order to do a matrix multiply? That is a great example of how the proliferation of new accelerated hardware presents an imminent threat to usability. Even today, optimizing code to run on GPUs is still much harder than optimizing code on general purpose hardware. And the number of ways that you can shoot yourself in the foot are much higher. Any potential for a 10x improvement comes with a non-trivial risk of an accidental 10x slowdown. In fact, we're already seeing clear evidence of the increased complexity, with now thousands of operators being in use and lots of time spent on writing and optimizing those operators. Plus, there's a technical burden of leveraging all of those operators, knowing when to use which one. The breakdown of those operators is also pretty interesting. The explosion of operators tends to be happening for non-convolutions. There are two ways to look at that point. One, it shows which part of the picture is causing the explosion. And two, digging deeper will tell us whether there are some heavy hitters that we should focus our time on optimizing. Okay, so that all sounds very scary and packed with work that needs to be done throughout the software system's layers. So now what kinds of things are we doing in FAIR to help, and what work is left to be done? Well, if we want accelerators to succeed, we have to connect the dots between the usability experience that people demand and the capabilities that specialized accelerators provide. Meanwhile, we saw a huge gap in investments in the broader AI compiler space, where I don't just mean code generation, but everything from new language features to automatic code generations to domain-specific libraries and tools. Investments in this space need to keep in mind the features that made PyTorch successful in the first place: simplicity, ease of use, usability, even if it comes at a slight hit to performance. So let's talk about some of the investments we've made or are making into AI systems thus far. First, we built PyTorch. We built TorchScript to go from Python programs to optimizable graph representations. This allows production teams to leverage the ease of use of PyTorch, but then create serializable and optimizable models. TorchScript has gained traction both within Facebook and outside of Facebook, as highlighted in previous year's PyTorch developer conferences, where it was highlighted by production teams at Uber, Lyft, and others. Another investment we made within FAIR that you may be familiar with is Tensor Comprehensions. The goal of Tensor Comprehensions is to lower the barrier for writing high-performance code in order to balance usability and performance. Tensor Comprehensions is really two parts. It's an easy-to-use front end for authoring operations, and it's a polyhedral optimizer for generating performant GPU code and auto-tuning for specific input sizes. Following along these same lines, we've recently begun to investigate new ways to express the functionality of certain operations in a more intuitive fashion, which we've tentatively called Tensor Statements. The focus here is purely along the lines of usability and reducing friction. Recall that the model for Tensor Comprehensions was that the user wrote the inner part of a loop nest, and the system would infer the loops. For things like matrix multiply, this was simple. But convolutions would get complicated because you had to manually calculate the indices and handle boundary conditions. So the idea behind Tensor Statements is to expose an API that is one-to-one with how people think about neural network operators. For convolution, this means introducing the concept of convolving or sliding one dimension across another. And for viewing or shaping operations, this means introducing explicitly named indices and talking about how those indices change. So let me provide an example to illustrate this. As you may know, there's a lot of related normalization layers: batch norm, instance norm, group norm, layer norm. They all show the same normalization pattern, but they calculate their averages and standard deviation over different dimensions. It's hard to understand this from the PyTorch code, which just gives the name of the operator. Tensor statement notation makes this clearer by making the dimensions averaged over explicit. In batch norm, we calculate one average per channel. This is an average computed across the batch and across the spatial dimensions, h and w. Descriptions of batch norm typically note that how it averages over the batch, but they normally don't mention that the average is per channel, rather than, for instance, taking a single average or a per pixel average. Other norms explicitly try to avoid averaging over a batch because it makes it difficult to do inference when no batch exists. But they choose different dimensions to normalize. From the computation at the bottom, we can see that the instance norm computes an average for each instance n and each channel c. That can be thought of as doing the same thing as batch norm, but not across the batch, hence the instance name. The distinctions of these two types of normalization become clear from the code itself, which directly ties into our goal here, which is improving usability and understandability of the operator code. As I mentioned earlier, tensor statements is a new concept that we're experimenting with, so stay tuned for more details on that. Aside from the front end, we also have several efforts underway in the traditional AI compiler space. We have multiple parallel efforts focused on model optimization and automatically generating backends across multiple systems architectures where the goal is to rival handwritten code generation techniques. One direction I'd like to highlight that emerged organically when we brought together several researchers with expertise in both systems and machine learning is that they immediately started looking at solving many of the tricky systems problems they were encountering with machine learning. So this falls under the related topic of ML for systems. In fact, I'll highlight some of the exciting progress we made in this space very recently. As a reminder, all of the ML frameworks, they allow users to describe neural networks using a high-level language, and it's up to the compiler or interpreter to lower that into a form that can be executed by the hardware. In order to generate that efficient low-level code, several challenging optimization problems need to be solved, including scheduling, resource allocation, code generation. All these techniques need to deal with extremely large solution spaces. So some solutions will start by pruning the solution space to reduce the set of candidates or leveraging handcrafted scheduling patterns. Instead, we leverage techniques inspired from reinforcement learning. We frame the problem as a tree of decisions where we need to find the optimal path from the root of the tree to one of its leaves. And we then rely on a value function to tell us how fast the neural network can run given a partial set of decisions, assuming that we make optimal decisions for all the remaining decisions. So given this value function, we can simply apply a greedy policy in order to make local decisions that are globally optimal. In one of our latest papers, recently released on arXiv, we evaluated the accuracy of that value function, as well as the resulting performance of the optimized models. And the results were very promising relative to the existing implementations in PyTorch, TBM, and Halide. Ultimately, these results meant that the solution is fast enough that it can be used by a machine learning researcher without interrupting their workflow. And yet it still manages to find efficient solutions that decrease the time needed to run a model, which can help increase the pace of ML research. Of course, the challenges that threaten usability on the back end don't end with code generation. The interconnection between the compute elements, which can range from near to multi-node hops, also needs to be hidden from the end user. So to help that scenario, we developed and released TensorPipe as part of PyTorch 1.6. TensorPipe is a tensor-aware point-to-point communication primitive that abstracts away all of the communication complexities and the protocols of remote procedure calls. TensorPipe is intended to complement the current primitives for distributed training in PyTorch, like glue and MPI, which are collective and blocking. And then finally, many of the features and experiences you want to provide are domain-specific. So there's always been a huge appetite for libraries that target common operations within a domain. FICE, which is Facebook's AI similarity search. This is a library that allows developers to quickly search for embeddings of multimedia documents that are similar to one another. FairSeek is a sequence modeling toolkit that allows researchers to train custom models for translation, summarization, language modeling. Pythia is now called MMF. This is our open source modular deep learning framework for vision and language multimodal research. Detectron 2 is a platform for object detection and segmentation, which is built to support rapid evaluation of novel computer vision research. So within FAIR, our charter has always been to do our research in the open and for the benefit of all and encourage others to come along. So to facilitate that, throughout this process, we've been focused on releasing reusable components to the community to help democratize the work in this space. Some of the ways we've been trying to remain true to that mission include releasing nearly everything I've told you about today as open source and through GitHub, either already or very soon. We've been prioritizing publishing all of our findings at conferences or on archive, leveraging Facebook's papers with code links to our sources whenever appropriate. We've also been heavily involved with MLPerf, which is a consortium of AI leaders across academia and industry who have gotten together to standardize a set of machine learning benchmarks for evaluating hardware and software. And one final component that I'm excited to share stemmed from the fact that we had so much fun playing around in the reinforcement learning for compiler space. We created and are releasing the SysML Gym, which is an easy-to-use playground for experimenting in this space. So the goal here is to democratize research into leveraging reinforcement learning for many of the canned computer compiler problems, and to enable people to be able to focus on exploring ML solutions to those problems without worrying about setting up the entire compilation environment. Okay, before I wrap up, I wanted to acknowledge that we're certainly not alone in resolving the underinvestment in some of these exciting spaces. And I want to give a quick shout out to just a few of the related efforts that have caught my attention. Contributions like Microsoft's DeepSpeed, which is a deep learning optimization library for distributed training, or Halide or TVM for exploring the compiler space, or Google Brain's investment in applying ML to systems problems like data structure design, optimization, or even processor design. Or Google JAX, which is a heavy focus on usability. Or other language-related efforts like Julia or DiffTaichi from MIT. Each of these efforts corresponds to a unique part of the problem space, or they take a unique approach, but have tried to keep usability top of mind while doing so. So, to wrap up, I want to underscore that the very feature that I feel has led to the success of PyTorch has been usability. But this is a lesson that throughout history, we have a terrible track record of remembering. And we love to resort to complex solutions that prioritize performance over usability. This is a lesson that we need to keep in mind in the entire end-to-end AI framework ecosystem. I talked about several trends like operator explosion that make me worry that we're headed toward another usability crisis if we're not extremely careful about how we design solutions throughout the end-to-end framework and ecosystem, from compilers to tools to libraries. There's a lot of work to do, so let's all focus on solving these challenges together, but agree not to forget the key lesson of focusing on usability above all else. Thanks so much for listening, and enjoy the rest of the conference.